Artemis 2's flyby is bringing back more than pretty moon postcards. The crew has been filming jagged, unfamiliar landscapes, brief flashes of something striking the dark surface, and even a total solar blink seen from lunar space. Behind the scenes, scientists are obsessing over what these images might reveal about hidden patches of usable water ice, if they exist where the models predict, and whether future crews can actually reach them. In this video, we'll decode what's really hiding in those frames, and why it could change how far humans can go next. Let's get started. As Orion curved around the moon, the view shifted from the bright, familiar near side to a darker, more rugged landscape, with fractured terrain and chains of craters fading into deep shadow. Low-angle sunlight sharpened crater rims and exaggerated slopes, revealing textures and subtle tone variations that usually vanish in overhead images. The crew followed a structured schedule, rotating through observation shifts to photograph basins, crater fields, and shadowed regions under specific illumination angles, maximizing what each pass could reveal. During this window, they reported brief flashes on the surface, interpreted as small meteoroid impacts striking directly into the regolith in the moon's airless environment. Tracking these flashes helps estimate how often the surface is being reworked, and how stable future landing and operation sites might really be. As Orion slipped behind the moon, communications dropped out, but observations continued. When contact resumed, astronauts described a solar blink, where the sun was briefly obscured by the moon, followed by Earth rising above the lunar horizon, lighting that sharpened the boundaries between sunlit terrain and permanent shadow. Those shadow boundaries, especially near the poles, are critical. Permanently dark craters can trap and preserve water ice. Seeing how shadows fall and how complex the surrounding terrain helps refine where usable ice might exist and whether astronauts could realistically reach it from sunlit ground. The scientific importance of Artemis 2 lies in connecting these observations to existing theories about lunar water. Scientists believe water may exist in permanently shadowed craters near the moon's poles. These areas remain extremely cold, allowing ice delivered by impacts or formed through chemical reactions to remain trapped over long timescales. However, knowing that ice might exist is only part of the challenge. Understanding whether it can be accessed safely is equally important. Terrain plays a critical role. Some shadowed craters are deep and steep, making them difficult to reach. Others may contain ice, but lack nearby sunlight for power generation. Artemis 2 observations help refine how sunlight interacts with crater walls and surrounding terrain. By examining these patterns, scientists can identify locations where ice may exist close to areas suitable for landing and operations. The presence of water on the moon also has broader scientific implications. Ice deposits could preserve records of early solar system material. Because the moon lacks erosion and weather, ancient layers remain intact. Studying these deposits could reveal how water and volatile materials moved through the inner solar system. This information may help answer questions about how Earth acquired its own water. Artemis 2 also contributes to understanding human performance in deep space. The crew operated beyond Earth's magnetic protection, managing communication delays and extended observation periods. These conditions influence how astronauts conduct science and maintain situational awareness. Learning how crews perform in this environment helps prepare for missions targeting remote polar regions. Another important aspect is trajectory testing. The spacecraft followed a looping path around the moon that allows safe return to Earth. Executing this trajectory with a crew on board demonstrates navigation precision and timing. This experience supports future missions that will transition from flybys to surface operations. These scientific goals are interconnected. Terrain observations support water detection theories. Human performance testing supports long-duration missions. Navigation testing supports future landings. Artemis 2 brings these elements together. turning observational data into practical knowledge for upcoming exploration. If accessible water ice exists, the moon's role in exploration changes significantly. Water can support life support systems and be processed into hydrogen and oxygen. These elements can be used for propulsion and breathing systems. Using local resources reduces dependence on supplies launched from Earth and allows longer missions. Future Artemis missions are expected to target polar regions where these deposits may exist. Artemis 2 observations help refine potential landing zones by improving understanding of terrain and illumination. Selecting locations near possible ice deposits while maintaining safe landing conditions becomes the next step. The implications extend beyond individual missions. A lunar presence supported by local resources could serve as a staging point for deeper exploration. Missions could launch from the moon using locally produced fuel, reducing mission complexity. Technologies developed for extracting and using lunar water would also apply to other destinations. Artemis 2 also demonstrates operational readiness. The crew conducted coordinated observations, handled communication blackout periods, and navigated lunar space successfully. These achievements build confidence in human missions operating beyond Earth orbit. Each element reduces uncertainty for future landing missions. The imagery captured during the flyby will continue to be analyzed. Scientists will compare shadow patterns, crater geometry, and surface brightness with existing models. This process helps refine maps of potential ice-bearing regions. Over time, these maps guide mission planning, instrument placement, and landing strategies. The moon begins to shift from a distant target into a location where resources, operations, and infrastructure intersect. Artemis 2 does not establish a base, but it provides information that supports decisions about where such efforts might begin. The mission's observations feed directly into planning for sustained presence. Artemis 2 is revealing a moon shaped by deep shadows, rugged terrain, and possible hidden ice. Those observations are narrowing where usable resources might exist, and whether humans can reach them. What looks like a flyby may actually be the first step toward living and working on the moon.